Rated flow is required in sizing the plant, both canal and penstock, 4-bay tank, and all these component size will be determined by the requirement of the size of the rated flow. So, rated flow is an important parameter, and it is decided based on the water availability in the river, flow rate in the available in the river. So, as usual, this is our structure, our way of configuring a small hydropower plant. So, we have to know what will be the water flow rate that we can use from the river, cubic meters per second, that we can use in the small hydropower scheme, because our power generation depends upon Q, rho, G, H. H is a parameter depending upon the water height from the turbine level, and Q is the water that is coming into the canal, coming into our project, right. So, that now we are discussing how to determine Q for a given project, right. But before going into that, I would like to show you how to obtain this relationship of the power equation, because that is also important in this exercise, right. So, here you can see. So, we are looking at that water carrying a potential energy in the 4-bay tank, this canal brings water here, and we have the penstock here, and we have the turbine here, and water jet goes and hit it, right, and rotate it. And so, our head is the top water level here and to the jet level in a high head project, right, and water flow rate is water that is flowing in the penstock, cubic meters per second, H is in meters, right. So, the potential energy here is, we know, mgh, right, mgh, that is the energy that it carries, as we know from the fundamental equations. E equals energy stored in the water is mgh, and we know the power is dE by dt, right, dE by dt. So, if you make dE by dt of mgh, G and H being constant, it is dm by dt into gh, right. dm by dt is mass flow rate of water, right, mass flow rate of water, dm by dt, which is equal to q into rho. I have used the simple q here, q into rho. You can see the units, q is in cubic meters per second, rho is in kilograms per cubic meter. So, cubic meters will cancel, it is kilograms per second, right, kilograms per second is dm by dt, right, mass flow rate, right. So, you just replace dm by dt with q rho, then you come to this equation, P equals q rho gh, but at each energy transition there is a loss. To accommodate that, we introduce this efficiency term, because ideally you cannot transfer all the potential energy to kinetic energy in the turbine, right. So, it will be q rho gh multiplied by a efficiency factor, because otherwise 100% transfer is not possible, right. So, the overall efficiency is penstock efficiency, turbine efficiency, generator efficiency, transformer efficiency, and transmission line efficiency all together, if you take the entire project, right, entire project. So, therefore, this is the final equation for hydropower generation, whether it is a small hydropower project or large hydropower project or pico hydropower project, same equation will apply, right, same equation will apply. Now, if you look at Q, it will be varying. Q is the water flow rate in the river, right, which can be diverted into our canal. You can see it can go up high, maybe 5 cubic meters per second, or it can be low, say 0.5 cubic meters per second, or in between. right. We can't expect river to have constant flow, right, because it depends upon the upstream conditions in your catchment area. When it is raining, maybe it is maximum flow, and now it is 1 week, 2 weeks no rains. So, the flow rate will go down, and in the dry season it will be very small. So, this is time, days of the year, right, maybe 365 days here, for 1 year how the change is happening. So, this is a time series. So, this is a time series. So, where shall we say our plant be designed for? Rated flow here, or rated flow here, or rated flow here. I will call it QR1, QR2, QR3, right. So, how can we decide? If we use QR1, which is a high value only during this period, and during this period your plant can run on full load, because rated flow is available only during those small periods, right. And if you select QR2, you can run a longer time at the rated capacity. See, the number of days your plant can run on rated capacity is more. If you use QR3, right, then much longer period you can run your plant on full load, because your plant full load will be efficiency into Q rated rho G H. H will be a constant almost, right, and so the QR will decide the plant capacity. Whether you call it here it may be a 4 megawatt plant, this may be a 3 megawatt plant, this may be a 2 megawatt plant, right. So, the smaller you select your rated flow, smaller will be your plant capacity, but the duration you can operate will be longer, right, duration you can operate will be longer. Therefore, which one we can decide, that is a question, right. So, to answer that question we must convert this to a flow duration chart, right, flow duration chart. So, we will come to that, right, we will come to that. Now, we have come to we have done a lot of studies and we are convinced that there is a good project. Therefore, this is right time to employ a professional hydrologist, right, professional hydrologist into our estimation, right. So, now what we do is we will show a professional hydrologist. We are going to do a hydropower project at this site. This is a water diversion location we have planned, and the catchment can be calculated in this area. Please show us how much water will be available at this location for diversion here at this point, the diversion, right, on a daily basis. That we are asking him do a study with his expert knowledge and tell us what will be the available Q, right, on a daily basis for 365 days. So, this is for a project that we did in Sri Lanka. So, we have given this location, diversion location, to a hydrologist. So, this is the report he submitted to us after his study. He took about 1 month for the studies with his expert knowledge. So, I will not read the entire report, but I will just read some initial lines. The proposed project is across Lemastota, a tributary of Valley Oya, which is in turns the tributary of Walave Ganga. These are names of the rivers. The site can be reached from these places and so on. So, he says, and then he says objective of this study. The objective of this study is to determine the long term flow regime of this catchment to assess the water availability from available hydrological data for hydropower development. So, that is the objective of this study. That is what we have given him, the assignment, right. This is a paid assignment. So, he will give us all these data. So, then he goes on hydrological data and so on. I will not waste time here, lot of time to read this report, but I will tell you what is the final outcome of study. He is using his expert knowledge and some mathematical models that he is used, he call is, you can see, I will read here, item 5, mathematical model. The correlation of daily rainfall and evaporation with the corresponding stream flow rates are interlinked in a mathematical model. In this study, NAM model developed by Danish Hydraulic Institution of Denmark was used to generate data. So, that is his expert area. So, he is using various models etc., to determine the daily average flow rates that can be expected depending upon the available data, right. So, he has used you can see now under for methodology, right. It says, therefore, model parameters were selected with experience in modeling similar catchments to generate stream flows for 30 years from long term rainfall available at Haputale from 1970. So, he has used data from 1970 to year 2000. We did this study in 2002, right. This report was generated somewhere there early 2000, right. So, he has used 30 years data, right, for this his model. Then he goes on his expert areas, data generation, flow duration data etc., right. And then he say low flow analysis. I am just showing you only the titles. Then the flood study, he says 50 years and 25 years flood study, because that is important for us to keep the powerhouse level. If the powerhouse we keep below the flood level, some bad year in a rainy year, our powerhouse can go underwater. Therefore, we ask him to give us what will be the maximum expected flood level at the powerhouse location. So, that also he include in his study, right. Then he goes on to say interpretations and various things, right. So, this is the name, this was done in 2004, right. Name is G.T. Dharmasen. He is a retired person from the irrigation department. So, they know all the historical data, they have the access to data, and they have done all this modeling and all these things. So, they are the experts, right. You remember that I said some other time we do an approximate calculation, that is approximate, right. Not we can't, if you go with approximate calculation to raise a bank loan for the project, bank will ask who did the hydrological study. If the hydrologist is not acceptable to the bank, bank will say no, we can't give a loan, because your data is not dependable. So, you must have a reputed hydrologist to do the hydrological estimation. Then you can tell the bank we use such a person's predictions for our energy calculation. So, we can depend upon that, right. Okay. So, finally, with this report he will give a data set like this. So, he will give us table like this. I will go to the bottom later. You can see it is flow data, units in cubic meter per second. Catchment area also he has put 17.9 square kilometers for this particular project. So, he gives for every month, he has started with October rather than January, October, November, December, then January, February, March up to September, right. And now, he gives what can be the expected flow rate for each day of the month. October 1st, he says you can expect 3.354 cubic meters per second flow rate. We assume for the day it is constant, right. During the 24 hours we assume it to be constant, it might be slightly varying, but we assume it to be constant, right. So, and second 2.5, third 1.8, that is going down, right, and going down on 10th of October we can expect increase, right, because maybe the next monsoon starts and so on, right. And so, this is depending upon the 30-year historical data that he has worked on, but based on that he says this is the best approximation, right, best approximation. And he goes like this for all the 31 days of the month, right, and for the other months, some month November and so on 30 days, right, and February 28 days and so on. So, he gives the start. So, there ends his business, right. His work is over from here. So, we have used the hydrologist to get this table, and from this point onward this data we must use to determine what should be our rated flow rate, and also how much energy we can annually generate. That is the business of a hydropower engineer. That is what we are learning from this course, right. How to use hydrologist data to go on and size our project, that is determine the Q flow rate, rated flow rate, and then each day how much energy we can generate, and also the capacity, what should be the plant capacity, etcetera. We should be able to calculate that. We will go through and see. Here the same table, right, same table, right. Here there is an additional term here, 75% probable daily flow rate. So, he says these are his 70, the probability of these occurrences are 75% as per his model. You can see. So, I have done some calculations here. I have put zeros for the non-existing dates, so that the table is more calculable, and I have also calculated monthly average flow rate here. You can see average flow rate. So, I have averaged all the 30 days here column, you can see. Okay. Okay. Now we have to handle this data set, right. So, some statistical knowledge is required now, because we can't, they are all, right, different numbers depending upon the. So, we will put them into some ranges, right, pick them, put them into some ranges. So, when I say 0 here, 0 and say 0.05 here, I mean it is 0.0 to 0.05, right. So, when I say 0.05 here, I really mean 0.00 to 0.05, right. So, this class, this range, I mean I put a single number, because otherwise I can't do calculations with this number if I put a figure like this. So, here it means 0.05 to 0.10, that class interval or range, right. So, you can see every number is a range, I am putting it here, right. So, I just put the n number only, right, n number only, right. So, the size is 0.05, because I want to use this for calculation, that is why I put a single number here rather than the range, right. Okay. Now, I want to count the number in this range 0.05 to 0.10, right, from that data table. How many points are here in that range, and put the number here, frequency column, right. You can see up to here there is no, but see there are 7 zeros, because there was number of months was not ending on 7 months. So, therefore, maybe on February 2 or 3 days were not there. So, altogether there are 7 months with zeros, which I have put purposely, right. Not hydrologists did not have zero flows on any date, any physical date, but I put zeros for the non-existing days, right. That is why the 7 zeros are there. Then in this range there are no any numbers, but 0.55, that means 0.50 to 0.55. There count the maximum range is there, maximum number are there, right. 183 points are there in this table, in that range, if you count it here, right, if you count it here, right. So, likewise we can count all the numbers and put here, but to do it manually it is very difficult, right. To count all the 365 data points and pick them up and put here is not possible. So, here we can use, therefore, there is a command in Excel called frequency command in Excel, right. Here you can see. So, frequency, data array and bins array, where data array is the range of your, I will just open it, maybe some of you are already familiar, right. So, I think you can go and study this, right. You can go and study this. How to do it I will tell you. I just want to, I also have forgotten there is a sequence of sequence to press some buttons. Yeah, control shift enter, I must remember, control shift enter, we have to press. Okay. Now, the problem is how to count these data points in each class interval, right. That is a manually you can't do it. Therefore, we intend to use the frequency command. So, I have put, you can see here the frequency command, I do not know whether it is too small for you, right. Frequency command I have put it here. So, I will show you how to use it again, right. I will press freshly. Put the number. So, when I go to this cell, right, I will select the entire range here, range of class intervals I have selected. Can see there are class intervals I have selected up to 8.2, that is 8.15 to 8.2 also the last class interval. So, I will select that plus one more, right, plus one more, and then I will type start plus, right, I will start typing frequency QUENCY and open bracket. Now, when as I open bracket, it gives a hint here, frequency, data array and bins array. Bins array are the class interval array, right. Data array is the data array that we have, data set that the hydrologist has given. So, I go to flow data one, give the data entire array here October 1st to September 30th, 31st. The 31st is not there, but theoretically we have put zeros for the 31st here. I will not give the average values here. This is the data array, right. This is the data array, entire data points in the data table that was given by the hydrologist, right. And then I will put a comma, and now it wants the bins array. Bins array are the this class interval column. Here class interval column, and now I will close the brackets, close the bracket. Now, we have to press 3 buttons together, control shift enter together, control shift enter, then it counts everything and put it here, right. Then it will count all the data points in that array data set and put them here, right. That is the easy way of picking up this, otherwise you can't do it manually. So, you can study frequency command separately and get this knowledge and do it as I said, right. So, then I have calculated cumulative frequency here, that is frequency plus the next one. So, up to here it is 7, then 7 plus 183, 190, 27 plus 190, 217 and so on. So, I have put all the values here, right, because there are 372 data points, because we have put zeros for 7 days, 365 plus 7 days come, because we have put zeros for non existing days, right. That is why it became 372. And then I have calculated probability of every frequency, right, that is frequency divided by 372, right, for this number of days, what is the probability, right, 183 divided by 372 here, right, E12 divided by 372, and likewise I have calculated, right, here. And then I have, because I want to get a certain shape of the graph, I have calculated 1 minus p and also percentage of that multiplying by 100, right. Now, I draw a graph between this last column and the first column, sorry, second column here, column C, right. I draw a graph between column C and column H, right. Then it happens to be a graph like this, flow, we call it a flow duration curve, right. So, for example, the vertical axis is flow rate, horizontal axis percentage time, right. So, for example, if you take any point here, right, for example, 1.5 cubic meters per second is available for, let us say, 4, 8, maybe about 12% of the time of the year, right. If you take 0.5 cubic meters per second, flow rate is available for about 40, say 48% of the time of the year, right. So, rather than the time series curve, this is more useful for us, right. We know, because in the time series curve, you can see. So, to know how long the plant can run at QR2, see, right, QR2, you have to draw lines and count the durations. It is very difficult, right. But when you have the flow duration curve, if you select any flow as the rated flow, you know how much is the percentage time of the year that you can run at that flow, right, you can calculate. But if you select a very low flow like 0.5, you can see 0.5 or even less, say 0.4, then almost throughout the year you can run the plant on full load, but your plant will be very small, right, plant will be very small. And if you select, say 1 cubic meters per second, right, 1 cubic meters per second, you can run about, say 18% of the time full load, and balance 82% of the time of the year your plant will be running at a lower load than the rated flow, right. That means, you have spent money and have a higher capacity, but you can use only for 18% of the time the full capacity, right. And if you put what, say 2 cubic meters per second as your rated flow, I will put these numbers here, I do not know whether I can draw here. So, you can see if I select 2 cubic meters per second, my plant capacity will be very high, right, because P is equal to Q rho G H, rated capacity will be much higher, right. But you can run only approximately 8% of the year, each side is 4%, 4, 8, 12, 16, 20. So, about almost about 7% or 8% only you can run on full load. Your plant is big, but the number of days you can run on full load is 8% of 365, right, that is less than about a month. All the rest of 11 months you will be running on lower capacities, right. And therefore, the decision on the selection of the flow duration curve will depend upon how much is the tariff you are getting. If you are getting a very high tariff, you can even go for 2 cubic meters per second and have a very big plant, right, but it can run only a few days, maybe 20-30 days on full load, but you can afford to have higher capacity spent for a larger plant, because your tariff is high, you can still afford to do it. But if your tariff is very bad, very poor tariff you are getting, then in that case you can't do that kind of work, then you will have to go for a lower flow duration curve, rated flow, lower rated flow. So, that your plant is now having lower capacity, plant cost will be lower, because you can't afford to have extra capacity, tariff is poor. Therefore, depending upon tariff you will select the plant. Or on the other hand, I can say another way of deciding this is to select maybe 3 or so number of the rated flows and theoretically design 3 plants and estimate their project costs, and then do a financial analysis and see which capacity brings the, or which flow the rated flow corresponding to rated flow will bring the highest return on investment. If you go by IRR, which will bring the highest IRR, and then accordingly decide the flow duration curves location where you should have the rated flow, right. So, I will go back to again here, you can see. So, in the flow duration curve, so whether to go for Q1, Q2 or Q3 as the rated flow will depend upon how good your tariff is or how your project costs are. If your project costs are low, because labor is cheap, equipment you got cheap, and also the construction material costs were cheap. If your project costs low also, then you can justify a higher flow rate, rated flow rate, because your then return on investment is the deciding criteria. Whether the plant corresponding to Q1, right, will bring the, I think hope you are familiar with the terms like return on investment or internal rate of return. These are financial terms. IRR 1, this is IRR 2, internal rate of return. Q3, IRR 3. So, which is the better one? Which is bringing the higher financial returns? Then select that one as the rated flow. Sorry, right. So, that is the criteria on deciding the rated flow of a small hydropower plant, right. So, in Sri Lankan tariff, projects in this range are justifiable, maybe 15 to 20% range. It depends upon the situation the country or your state is offering, the tariffs offered by them. If the tariffs are very good, then you can go for this side, right. If the tariff is bad, lower, right. So, the ideally the rated flow should be decided by financial consideration, which project brings the higher return on investment, right, which project brings the higher return on investment. So, in Sri Lankan condition, we know it is somewhere here because of the tariff paid in Sri Lanka, but I can't recommend that for you, right. So, you must find out from the flow duration curve what should be the one that is applicable for you depending upon the return on investment after doing a cash flow analysis, right, after doing a cash flow analysis, which a financial expert can do, again accountant can do, right. The selection of QR at lower exceedance will result in a power plant with lower plant factor. For example, in the above example, if QR equals 1 cubic meters per second corresponding to an exceedance of 12%, plant will operate only 12% of the time during the year at rated capacity. During the balance 88% of the time, plant will operate below the rated capacity. Therefore, the selection of QR will depend on economic considerations such as tariff, cost of plant construction, etc. If the tariff is high, even a lower plant factor will be economically viable, right, economically viable. So, you can go for a higher rated flow. Now, we know the rated flow rate, therefore, we can calculate rated plant capacity, right, and we have here I have used a term called net head, H net, because there are losses in the penstock, right. So, we introduced a term called gross head, right, minus losses, head losses, and then calculate net head, right. Therefore, net head is equal to gross head minus head loss. Head loss we will keep generally about to 5% of the available head, right. We will keep it less than 5% of the available head in our penstock design, right. Penstock will be designed, its diameter will be decided, and so that head loss will be not more than 5% of the available head, right, available head, right. So, gross head is the one that you can decide from the physical surveying or by looking at the contour lines. Theoretically, looking at the 1 to 50,000 maps contour lines, you can say upper contour line weir at the weir location contour height is 800 meters, at the powerhouse the contour height is 700 meters. Therefore, the gross head is 100 meters, gross head is 100 meters, from which you have to deduct the head losses to get the net head. So, this will be then your rated plant capacity, right. So, you can call your project 5 megawatt, 3 megawatt or 1 megawatt after this calculation, after deciding the rated flow, right, and deciding the head loss, so that you can get the net head, then you know exactly what is your plant capacity. So, once you, so there was a question some other time, how you decide the project, the turbine type for the project. We are going to address the turbine types later, but here is a answer for that question. You can see here is a turbine application chart for hydropower plants, right. You can see here the horizontal axis is flow rate Q, right, cubic meters per second. Vertical axis is net head, right. So, you can see if our project has a flow rate of, say, this is in logarithmic scale, right, 3 cubic meters per second flow QR, right, and if the head is, say, 100 meters, then you come to a point like this here, somewhere here, right. And now you can see what type of turbines are suitable for your location, because this chart shows if you are here what type of turbines could be applicable. You can see now this location is lucky, red line is, red cage is Pelton turbines, right, and yellow cage is Francis turbines. You can go for either Pelton turbines or even Francis turbines, or even a Turgo turbine is possible. You are very close to the boundary, right, even a Turgo is okay, but you can't go for cross flow, right. You can't go for Kaplan, right, you can't go for Kaplan. So, this is a turbines application chart, right, typical turbine application chart. This is designed by doing various experiment by turbine manufacturers, like the specific speed of the turbine and other data they look at, and then they prepare the tables like this, right, and then this can be used by engineers for turbine type selection, right, turbine type selection. So, when we discuss about the turbine types in a separate discussion, we will go into more details. Here is the typical water cycle that we talked about earlier, right. So, what happens when the rain falls into your catchment area? Some will be evaporated, some will be transpirated, and wind will blow break this whatever the clouds into some other regions, and some will be taken into subsurface transfers, etc. Only a small amount will come to your river, right. That is what the hydrologist studied with his expert knowledge. Here is a more details about what happens when the rain falls on catchment area, right. And now, right, now you can see now hydrologist has given us data and we have determined this flow duration curve, etc., etc., right, etc., etc. Now, all these are estimations, right, all these data sets were estimations, right. Now, hydrologists also use 30-year data backward, and therefore, he predicted what can be expected, but in spite of that there can be very dry years, there can be very wet years. He has given the average expectation, right, average expectation. So, he can't guarantee every year you can get those flows, right, but now anyway there are uncertainties in this. He says 75% probable data set, right. Therefore, now once you have decided gone up to this thing, it is good to measure the water flow rate in your river now, and to have at least a few months, so at least 1 year's actual measurements to confirm whether the whatever the hydrologist has given now in agreement with the actual measurements, right, in agreement with the actual measurements. So, for that we will construct a measuring weir across the river, right, or else we can use an approximate method. Now, suppose you visit the site one day, right. So, you can that you can ask from the villager there how much is the flow rate today. He might say today is lower because it was dry these days, etc., and then you can measure it that day by approximate method. So, you can get the cross section of the river, right, by a stick you can measure at equal distance, and then using trapezoidal law, etc., you can for each trapezoid you can calculate the area, right, and then get the entire cross section, right, entire cross sectional area you can measure with an approximate method, by dividing into trapezoid or rectangles or whatever, depending upon the shape of the river bottom. You can get a villager to get all these measurements and approximately get the cross sectional area of a place, right. Then you can measure the surface speed, surface water speed. You can put a float, something to float, and measure the time taken to go a certain distance, right. But you can measure only the surface speed, you can't measure the speed will not be uniform, right. Average speed you can't measure, you can measure the surface speed by using a floating object. Take your watch and watch time 1 minute, what is the distance it has gone, and then you know the surface speed. Once you know the surface speed, you can use this approximate formula, average speed to be a constant time surface speed. This constant is about 0.6 for rocky beds. If the bed is rocky, rocks are there, then it is about surface speed multiplied by 0.6 will be the average water speed. If it is a smooth surface, it is about 0.85 times the surface speed. These are by experiments, right. Hydrologists have done experiments and they have come up with these numbers. So, where you measure this water speed, right, water speed, surface speed, multiply by one of these numbers depending upon the nature of the bottom of your river, calculate average speed, V average. Now, you have calculated the area, total area of the cross section of that location, and V into A will be your Q on that day, Q on that day, that the day you visited the place. And now, you refer that to your hydrologist data set, and you know the date, right, and you have measured this and see whether it will not be exactly matching, whether it is in the range. If the hydrologist has said it will be 1.8, and if you get, even if you get 3.2, okay, you are in the same range, but if you get 13.2, then there is something wrong, right. They must be tallying in the range, right. Therefore, if you get this, there is something wrong, right. So, if it is 3.2, maybe in this may be a rainy day, rainy year, you might get a higher one, but they are in the same range. So, you can be sure, you have some confidence that the hydrologist values are in agreement with the actual data, right. And also for the flow measurement, there are other methods like velocity head rods. There is a rod like with the cross section like this, we call it a velocity head rod. So, we keep it against the water flow, and then height will increase by hitting. When it hit here, water height will be a little high because of the speed, surface speed, and you measure that, and this head has been tested for this height against the surface speed in labs. So, if your height is h1, you can calculate what is the surface speed using this chart, right. The velocity head rod has been calibrated, and this chart, this graph has been produced, right. With that you can, this is another method of getting the surface speed rather than using the float method, right. So, this is, so using this also you can get the height. So, you can correct it. So, depending upon the previous equation, we can calculate the average speed using 0.6 or 0.85 depending upon the wet condition, once you get the surface speed. So, this is surface speed. And now, you are so the day you visited, now you took a measurement and you are happy, now they are in agreement, but this is not good enough, right. This is not good enough. Therefore, we will go for a continuous measurement, right. We will go for a continuous measurement. For that, we will construct a permanent, maybe a weir, measuring weir, right, measuring weir across the, maybe a place where the river is not very wide. We will select a place and construct either a rectangular, this is a rectangular weir, right. This is a V notch, what you call V type shaped weir. So, the water will flow across it, right, and the water height you can measure. You can have some markings here and water height can be marked. Here also you can mark here. Somebody can go there and every day take the measurement. This is marked here, what is the water height, right. And then using this formula, you can calculate the flow rate for that day, right. It depends upon the parameters of the V rectangular notch, or if it is a V notch, you can use this formula, right, and calculate that day's flow rate. So, you ask some village boy every day to take a measurement, and call you and tell, maybe once a week he will give you last 7 days, he will tell only the height. Once you know the height, you can do your calculation and find out what is the flow rate, right. So, that will make your the estimation will be checked further. What the hydrologist gave as the flow data, we will have a second check, because we are spending lot of money for the project, and if the flow data somehow is wrong, then our entire expectation of energy generation will be affected. Therefore, it is always better to double check, right. So, in the both projects we did in Sri Lanka under my this thing, we constructed this kind of measuring vias. So, this is in the one of the 2.5 megawatt project. Before doing the project, we had about 1 month 1 year's flow data, 1 year's flow data. Therefore, we were assured that the data set given by the hydrologist is dependable. And for the other project also, it was a little narrow, it's a narrow, bit, this is a narrow place, we could easily do it, but the other one was a bit wide. So, we had to do a bit of a construction. We used the natural features of the river also, right, and selected on a rocky place and constructed this rectangular weir, and we also got about 1 year's data before we actually invested in the project, and we could confirm hydrologist calculations are correct. So, I have published a book based on my experience called the Development of Small Hydropower Plants, Practical Information, and this is available in Sri Lanka, and so, but I just put it here, right, for your information. So, we will go along with the discussion on the design of penstock pipes for small hydropower projects, which is an important component in the design of a small hydropower schemes. So, the main task of the penstock is the intake water under pressure, to take water under pressure to the turbine. When penstocks are selected for small hydropower projects, following matters are considered: the diameter of the pipe and the pressure the pipe has to bear, the method of jointing, the length and the weight of the pipe pieces so that they can be handled at site, the maintenance requirements and the expected life, nature of the terrain where the penstock is erected, how quality of water, climatic conditions, quality of soil, etc. affect the pipe. So, these considerations must be made so that we do not have to that we make a wrong decision and be having a problem while the plant is in operation, because the penstock has to operate, as I said earlier, to 30-40 years, right. So, you can't replace it in between, which is very expensive, right. Therefore, we have to consider all these things in taking a decision. So, when designing a penstock, two parameters need to be determined: diameter of the pipes. Diameter of the penstock pipe should be determined to keep the head loss in the pipe to acceptable limits. So, we earlier said the plant should be designed to have a net head of at least 95% of the gross head, that is to keep the head losses limited to a maximum of 5%. Then we need to determine wall thickness of the pipe, because the wall thickness is required to bear the pressure. So, the pressure for the penstock will be highest at the entry to the powerhouse, because then you have the full head operating, and at the forebay tank pressure will be minimum. Therefore, your penstock need to have higher thicknesses at the bottom parts of the penstock, right, bottom parts of the penstock. In the diagram you can see in one of our projects how the penstock was under construction. So, you can see each piece you can't handle two heavy pieces. So, we limited each piece weight to about 2.5 tons maximum. So, that the people can handle them with manual means, because you have to align them perfectly before welding, right. You have to align them perfectly before welding, right. And also you can see this these pipes we bought from a company in Indonesia, right. They are spirally welded pipes, you can see here in the factory they are spirally welded, right, spirally welded and X-ray tested. The welding has to be tested using X-rays, so that there are no weak points or air pockets in the welding, because these are to undergo heavy pressure. If you have bad welding, then they might on the way result in leaks, water leaks later on. So, a pipe with smaller diameter will be cheap, but the head loss will be high, right. Smaller diameter means more restrictions for the water flow, therefore, more head loss, right, will be high, and due to the high water speeds, the pipe will subjected to high surge pressures when valves are closed, right. The head loss due to water flow in the pipe has two components, right, frictional component and turbulence component. Head loss due to turbulences and head loss due to friction. Friction comes from the surface, right. Turbulences come from the various other equipment we install in the pipes, maybe a valve, right. Valve, due to presence of the valve, water flow will not be laminar, smooth, right, it will be disturbed, some turbulences will be increased, right. So, head loss due to friction and head loss due to turbulences. So, head loss due to friction can be calculated using this formula. This is from hydraulic engineering, right. 6.3 into length into NV, N is the friction coefficient of the surface, V is the water speed, mean velocity, mean water speed, and D is the diameter of the pipe, capital D is the diameter of the pipe, right. So, this will be the frictional head loss, right, frictional head loss or head loss due to friction, and this friction coefficient for different materials are in this table PVC 0.009, because in very pico hydro projects, sometimes very small, maybe 5 kilowatt, sometimes PVC pipes are used as penstocks. You may have seen, I have seen some pipe, some plants, very small plants, they use specially manufactured PVC pipes for penstocks. Steel 0.012, galvanized steel has a higher, because galvanizing will increase the surface friction, surface roughness, right. Galvanized steel, concrete 0.12, right. Sometimes for a very small projects, heads, projects with very small heads, maybe large large water volumes, but pressure is low because of the low head. You can use concrete pipes, right, instead of a steel pipe. So, you can calculate frictional head loss using this, right. Turbulence head loss we have to calculate separately, right. So, the head loss due to turbulences can be calculated as K V squared divided by 2 G, where K is the you can see the loss coefficient, that is that different components will offer different turbulences. So, valves will have a different loss coefficient, bends will cause different turbulences, constrictions, when you change the pipe diameter from one to other, right, that will load D1 to D2, that is a constriction, will offer certain turbulences, and then when the water enters at the forebay tank, right, how it enters, whether it is a smooth connection or whether it is a rough connection, will cause certain turbulences, right. So, we will look at how to calculate each of them, right. Head loss due to valves, right, depending upon the type of valve, turbulences will be introduced. For spherical valves, I am sure you have seen spherical valves in your home sometimes, they do not have any turbulence, it is very smooth flow, right, but gate valves will have some turbulences will be generated. So, the coefficient they have found by experiment is 0.1, butterfly valves 0.3, right, more turbulences because of the presence of the turning parts there, right, butterfly arrangement, right. So, we can see in our project what will be the turbulences offered by our valves, for example, main inlet valve or whatever it in the penstock connected to the penstock, right. Then penstock due to the turbulences due to bends, when a bend is there, right, can see some turbulences can occur, right, because the water comes and change the direction, right, and also this is a welded place, right, there are many welding joints here, right. So, there can be turbulences. So, it will depend upon diameter of the pipe and also radius of the bend, right. So, with the ratio R and D 1, 2, 3, 4 this ratio, and for different angles, bend angles, right, different coefficient will come. So, we can from this kind of a table you can get the number for your project. So, you will have number of bends in your penstock. Penstock will not be straight, depending upon the land profile it will have both horizontal as well as vertical bends, right. You can't route it straight line, there will be many difficulties in taking it in a straight line, right. So, depending upon the land profile you will have, I will show you some photos later on, that you can depending upon your shape of the bend, at each bend you can calculate what is the offered loss coefficient. Then reduction of the diameter, if any place, if you have changed the diameter of the pipes, then accordingly you can depending upon the two diameters, right. So, you can calculate what is the offered turbulences coefficient for the loss coefficient for the creation of due to the turbulences. Then at the entry of the water in at the forebay tank. So, if you have your pipe like this, 1 very high coefficient, right. If it is flat 0.8, if it is a rectangular like this 0.5, if you can make it smooth, it should be smooth like this, then it is 0.2, right. So, it is important how water enters your penstock, right, how your water enters the penstock, otherwise turbulences will occur, right. Turbulences are energy losses. So, then you can calculate your total loss coefficient, right, and multiply by average water speed squared divided by 2g, that will be the total head loss due to turbulences, right, total head loss due to turbulence. Now, you calculate the total head loss, right. So, total head loss is Hf plus Ht. We will try to keep it maximum to 5%, but better to keep it in the range of 2 to 3%, right, say 3% of the head of the gross head. If the gross head is 100 meters, make it maximum of 3 meters, right, maximum of 3 meters. So, accordingly decide D, right. So, your previous formula they contain the term D, right, all these calculations will depend upon the D, right. So, your all these Ht and Hf terms will have the term D, right. Even here can see the term D is here, right, but they are in non-linear forms. So, you will have to put some typical values and select the one which is fulfilling this criteria. So, it is not a linear equation to solve, to the d to the power different terms. So, you can select from there are standard diameter, you can't select diameter of 31.1 centimeter, This is not produced by manufacturer. So, you are go to manufacturer's site or a standard and look at what are the standard diameters and select the nearest one for you and see whether it fulfills this requirement now, and accordingly select a suitable, because when you come to actual designs this linearity is not there. So, you will have to do some experimentation and trial and errors and then select a suitable diameter, right, suitable diameter. Then how to decide the thickness of the pipe walls, right. So, the thickness of the pipe walls depend upon the pipe material, what type of steel you are using, what type of other material, diameter of the pipes and the operating pressure on the pipe, right. Because the diameter of the pipe is causing that you can't handle pipes if it is the diameter is large and the thickness is small, then what will happen? The shape will change, right, when you handle pipes. So, you have to worry about that, right. So, the operating pressure caused by both the static pressure and the dynamic pressure or the surge pressure, right. So, the operating pressure is equal to static pressure is the H rho g, H is the height, water height, right. The pipe is subject to if the penstock is like this, depending upon the location, it is connected to the forebay tank, water level is here, from here how much is the head for this location. So, this at this location static pressure will be H rho g, right, and then the dynamic pressure is different, surge pressure, and the pipe is subjected to both, right, static pressure. So, when the pipe plant is shut down and all the valves are closed and so on, only the static pressure will act. But once the pipe plant is in operation and when you open and close valves, right, then dynamic pressures will apply. We have to look at what is the possible maximum dynamic pressure, right, maximum dynamic pressure. We should design for that, for the maximum dynamic pressure. So, in this deciding the surge pressure, we have to calculate what is called this wave velocity of the surge, right, and the critical time, right. The critical time is given by the length 2 into length divided by the wave velocity, right. The critical time is the one important one. You must avoid closing your valves, right. If you do it shorter than the critical time, you will have more surges, surge pressure. I am sure you have some experiences like this at your home. In the olden days, we had in the home water system valves where you have to rotate many times, maybe 10 times to close, 10 times to open. But the modern valves are not like that, just 90 degrees turn, right. Now, your closing time is much shorter, right. So, when you close and open these home valves, new valves, you will see the flexible cables in your bathroom will jump, right. That is because of the surge pressure created by quickly closing the valves, right, quickly closing the valve. This was not with the olden valves where you had to rotate many times. So, you do it take much more time than the critical time, right. So, no issue, but with the modern valves it is not like that, you close in maybe 10 seconds. So, that surges are generated and which will go and you can see it in the flexibles connecting your various wash basin supply to the main system. They are flexible wires at the corner, it will move because of your closing of the quickly closing of the valves, that is the surge pressure, right. To calculate that time, you can use this formula. This again from hydraulic books, right. The various terms are there. I have given this bulk modulus of water. Do not worry about these things. You can get these things from handbooks, right, handbooks, and then you have to only worry about the units. You have to put the correct units, compatible units, right, otherwise they will not match. So, the magnitude of the surge pressure that occur in the pipe when the plant is in operation depend on the rate of change of water flow due to operation of the valves or gates. If this change in water speed happens in a shorter time than the critical time, maximum surge pressure takes place. If the valve is closed instantaneously, the entire length of the penstock will undergo this peak pressure. When the time taken for closing the valve increases, a proportionate length of the penstock will undergo the peak pressure. If the valve closed in the critical time, only the valve will undergo the peak pressure, and so on. There are many parameters, but we do not have to worry about that. We calculate the peak pressure and design to that peak pressure. That is the possibility, because you know that what happens is, if you have this final water jet, right, your needle valve will be like this. From here you will have a needle moving up and down. So, this will be moving up and down to close and open the final jet, water jet hitting the turbine, right. So, this will go up and down depending upon your signals coming from the control system, hydraulics, and it will be operated by the hydraulic system. So, this water jet will go and hit the turbine blades, right. And so, the amount of water going will be dependent upon this movement of the needle valve, right. But you can see, due to some reason, needle valve can go and quickly instantaneously close the valve, creating a surge, right, due to some malfunctioning of the hydraulic system or due to some wrong signal, it can go and close instantaneously. Therefore, we must design for the peak pressure, peak surge pressure, right. So, the peak surge pressure is given by this velocity, average wave velocity, into change of speed. Change of speed we can take as flow rate, water speed here, right, water speed here, because instantaneously it can change to 0 if the valve closes instantaneously. So, we will take it as the maximum possible, right, and divided by G, and we assume this pressure is subjected to, the penstock is subjected to this pressure plus the static pressure, right, plus the static pressure, and accordingly design the thickness, right, right. So, it will not be uniform throughout the penstock, for the entire penstock. Therefore, we can't have continuously change in thicknesses. So, we will have some section to have say 8 millimeter thickness, in the next another section to have say 15 millimeter thickness, in the bottom part of the penstock to have maybe 20 millimeter thickness, depending upon. So, we will conveniently select what is available in the manufacturer's facilities, standard thicknesses and the diameters. We will select some optimally, because you can't buy pipes with continuously changing thicknesses, that is not practical. So, we will have to select some depending upon the length of the penstock, suitable thicknesses, so that your cost also goes down, and also your practical limitations are also there. And there are many practical issues in, you know, that when you are buying, okay, we will look at first the, you know, the total, this I have already given, right. So, you can get the total static pressure plus the surge pressure, and the wall thickness you can calculate from P d divided by S. S is a safety factor, right. Maybe you can use 3 or something like that safety factor for, because we do not produce in the designs, we do not use the limited value, the final limited value for practical operations. And also thicknesses, we will add some about 2 millimeters for corrosion allowance, right. We will, after calculating the thickness, we will allow about 2 millimeters extra for the future corrosion possibilities, because the pipes will corrode over the years. Therefore, to keep about 2 millimeters corrosion allowance is also practical, right. So, we can calculate the thickness using this method. Sometimes we will go for slightly different diameters for the transportation requirement, because suppose your diameter is 1.5 meter, right. Normally, we transport these things in containers, right. So, if you put them in a container, maybe you can put 3 of them, only 3 pipe pieces, right. So, it is a waste. So, your shipping cost will be much higher if you get it from some outside the country. Therefore, what we do is we have some section with a slightly smaller diameter, so that you can insert them inside the larger type, maybe about 2-3 centimeters smaller diameter, and then you have a small reduction and another diameter for some section, for the practical reasons like this, right. So, you have to worry, otherwise your shipping cost will be much higher, penstock will be, total cost will be much higher. So, normally we do this kind of arrangements to economize the shipping, right, shipping and transport, even ground transportation. Otherwise, you can put only 3 pieces in one lorry, right. Now, you can put 6 pieces and so on, right. Okay. Next one is we have to consider, when you are really installing these pipes, right, in the ground, what are the other supports that we have to give, right. So, on the first place there should be supports, right, supports for the penstock, and also anchors for the penstock, as we are going to see, right, later on. When you have a bend, when the forces change, there are dynamic forces and static forces, we will see them later. So, they will have an upward resultant at every bend. What will be the result? Under operation, the forces will try to take it up. Therefore, you must anchor it with concrete block, right, and the weight of the concrete block will depend upon the forces that are developed at bends, right. So, other than the anchors, on regular intervals you must have supports, right, carry the weight of the pipe and water, right. So, you can see the if the pipe weight is Wp per kilogram per meter, Ww for the water per kilogram per meter. So, they will have, you can see, total weight will have a component perpendicular to the pipe F1 and a component parallel to the pipe, right, between each support. So, this will have a component parallel to the pipe and perpendicular to the pipe, right. So, they have to be handled, they are significant numbers, because the weight of the pipe is about 2.5 tons and water will be having a substantial weight. So, all have to be borne by the supports, otherwise the pipe will deflect, Calculate this F1 and F2, WPW, this the angle is theta, cos theta and sin theta, right, 2 component, right, alpha, cos alpha and sin alpha, right, so one parallel, one perpendicular. In addition to when the pipes move due to expansion etc., a frictional force F3 will act on the pipe as well as the support, right. Now, you can see now these pipes, right, if the pipes are held at both places by anchors, right, when the temperature changes, that pipe will bend because of the expansion. This will happen especially when you empty the penstock for some repairs or anything, because when the water is there, it will be water temperature, right, maybe 25-30 degrees in our conditions, maybe even lower in some part of the country, right. But anyway, it will not change very much, even if the sunlight falls on it, the temperature will not change very much, maybe 2-3-5 degrees will change from the water temperature. So, the temperature range change will be insignificant. But when you empty the penstock, and when the sunlight falls on the empty metal, temperature can go up to 40-50 degrees because of the sunlight falling on empty penstock. Then if you are holding at 2 places, right, rigidly, pipe can warp, bend, right. Therefore, you must have a expansion joint. Expansion joints are normally kept at the just below the anchor here. Expansion joint will have a cut here, right, and a covering arrangement here with bolts and all that. theoretically there is a opening or gap in the pipe ends, and there is a means of leaks are prevented by seals, water seals, right, expansion joints, and thereby the pipe, when the expansion requirement occurs, pipe can expand upward, and the amount of gap will decide depending upon the expected expansion, right. So, expansion joints are there, right. So, therefore, we have to mind all these things, right, and accordingly design the penstock, right. So, then now what happens is, now what happens, now expansion occurs, right, and when expansion occurs, pipe will try to move this way, right, on the support, right, on the support pipe will slip, right. As soon as it tries to slip, a force will act on the support, frictional force, right. Therefore, your support should be able to withstand that force, otherwise support will propel or that feel it, and then it can be inclined or whatever, right. You have to calculate the frictional force that is possible on the support, and accordingly support should be. So, the supports will have these forces on one hand, these two forces will be acting on them, one is perpendicular, one is parallel, right, and then frictional force depending upon the perpendicular component into the friction coefficient, right, into the friction coefficient will act upon the support. So, we have to tell the civil engineer, in your design of your support you should take all these things into consideration, because he might not be aware of this penstock movements and everything, expansion and everything, he may or he may not, but we have to tell him these are the forces that will come, right, accordingly design the support. So, the support will have a good base, right, good base and sufficient reinforcement, right, to bear all these forces. Right. So, the friction, there are different friction coefficient, right. If the penstock is kept on a steel sheet, if you can put some grease also on the steel, it can be different, or you can put a nitrile rubber or something, then it will be different, and so on. Friction coefficient will be different, right. So, I have given some typical values here. Here in one of our projects we put nitrile rubber here, right, nitrile rubber, because otherwise what will happen, all the paint will be over the years will be damaged by the movement, right, and corrosion will happen there, and the pipe will get damaged, right. So, some people put steel plate and grease here, in here we decided to put a nitrile piece here, nitrile rubber piece, which is very strong. So, which will not prevent any damages to the paint, right. And here you can see supports coming up, here this has a big base, you can see, which will going substantially into the earth as well, right, because otherwise they will be moving when the penstock moves due to friction and other things, right. They should be able to bear the static weight, dynamic forces, as well as allow the movement, right, allow the movement. Typical values for these supports, right, some PVC pipes and for steel pipes, depending upon the diameter, these are some typical distances we keep between supports, 8 meter, 5 meter and so on. Due to practical consideration, we have them because to avoid any problems with the supports later on between damage, but these can be further optimized. Here is an anchor, right. Anchors are required, we will look at the forces later on. Anchors are required to hold the bends, pin the bends down to the earth, so that unnecessary forces cannot move the penstock, right. That in a anchor you do not need much strength, you do not need lot of reinforcement. What is needed is the weight, right, what is needed is a weight. So, we just put a few little reinforcement just to keep the concrete together, and then put the concrete inside, and sometimes we put what you call a plumb concrete, to economize. Plumb concrete is you put some concrete and put some rubble pieces, this rock pieces into it, because it is the weight is the matter, not taking much any other forces, that it should be weight should be enough to hold it down, penstock down. So, we call it a plumb concrete, like plums in a bun, we put rock pieces to economize, right, economize. But you know that practically when you are doing this, what happens is you ask the contractor to put concrete, rocks. Some of them, you know, that to economize they take wooden pieces from outside and put them also there, right. So, they do not understand the principle, wooden pieces they do not have the weight, right, but they economize by putting these things, because they do not have to spend on rocks. These things are done in the jungle, right. So, unless your quality supervisor is not there, these contractors will play all these things. So, you have to watch. So, quality inspection is also a must, therefore, in constructing these things in remote areas, right. So, the forces acting on the pipes, right. So, there will be the perpendicular component of the weight of the pipe and the water that will come into the anchor as well, just like onto the support. When the pipe moves due to expansion, the frictional force, right, that will also come on the penstock. The parallel component of the weight of the pipe from the anchor up to the expansion joint here. So, you can see now this anchor will have to bear, all the weight of this. Suppose the expansion joint is somewhere here, where the pipe is discontinuous and the upper anchor is here, right. So, from this point, from the expansion joint opening point down, right, all the weight of the water and its parallel component will come on the anchor, right, and the frictional forces, when the friction is acting on the support, opposite friction will be on the pipe. So, that will also be coming onto the anchor, and the weight of the water will be coming onto the anchor, right. So, all these things have to be considered, the perpendicular component of the weight of the pipe and the water between the two supports nearest to it, right, and when the pipe moves due to expansion, the frictional force, the parallel component of the weight of the pipe from the anchor up to the expansion joint above it. So, all these things you can easily understand, right. Then the forces due to static pressure. Now, you look at this piece of the bend, this piece from this straight part to the this straight part and the bend part. So, if you look at this bend part, right. So, this pressure, static pressure here will be acting on it, on this direction, and on the other hand from this side it will be acting on this, right. So, this part will have a net force in this direction, this static pressure will have a net force in this direction, which will have a resultant in this upward direction, right, which will try to take the bend up due to static pressure. So, this formula can calculate it depending upon various angles, right, and that is due to static pressure, right. And then water flow, due to water flow, right. So, can see the water flow will have a dynamic pressure, right. So, again in the same direction, right, Q rho V, right, with these angles, right. So, they will have a dynamic pressure in these directions and finally, an upward thrust, right. Again you can calculate using this formula, right, and so this will happen only when the plant is in operation, when the water is flowing, right, when the water is flowing, right. So, because of the change of the direction, water goes and hit this surface, right, and due to that a force upward is created, but you can calculate it using the change of this momentum, change of the direction of the moment of water, right. I will not go into showing this calculation, how to derive the formula, etc., which you can do it if you want by referring to a textbook, but you can use it, right. And here are some, so after taking into account all these forces and the properties of the soil, right. At the proposed location of the anchor, a suitable anchor should be designed and constructed. As name suggests, the anchor holds the pipe securely to the ground by its sheer weight. More than its strength, its weight is more important. Therefore, when building anchors, an effort is made to reduce the amount of steel reinforcement and increase the weight. A popular method of doing is to use a plumb concrete. Another problem the civil engineers face when designing anchors is when the bearing capacity of soil at the location is very poor. In that case, naturally the base of the anchor need to have a larger cross sectional cross section, but the available space as well as the increased cost become major concern. So, you have to optimally design it by taking into all these factors into account. Here is a large, can see anchor, because this place the soil was very bad. So, we had to design a large anchor to increase the cross sectional area of the bottom, so that the earth can bear it, otherwise it will go down, right. And also the bend was big, and you can see here the expansion joint here. This is the expansion joint. Always expansion joint is below an anchor, right, not on the upper side, then otherwise it will come tip down. Always at the upper end of the penstock between two anchors. Here is a bifurcation. Now, we wanted to put two machines here, two turbines here. Therefore, one penstock comes up to here and then it divides into two pipes, but then lot of forces will be developed because of the change of directions. Therefore, you fabricate the bifurcation metal pipe division and then embed it in a big anchor, that big anchor, and you can still see here the expansion joints, that in both cases. This is near the powerhouse where the pipes is to enter the powerhouse, right, to the two turbines. So, we have come to the end of the discussion on the penstock design. So, we have determined to determine the thickness and the diameter of the pipes on one hand. On the other hand, design the supports and anchors required for the installation of the pipeline. So, if we do not do it, I have seen some power plants where the penstock has been completely destroyed by the forces, and they have abandoned the power plant because they were beyond repair, right. So, they have penstock design and their construction, installation, all should be done in accordance with the applicable meeting the applicable standards and quality requirement after doing all the calculations. Okay, we stop there for the discussion, and if there are any questions, I can take a couple of them now.
Sir, can a single 4-bay tank can handle multiple penstocks?
Yes, yes.
Or we can build different 4-bay tank for that?
Yeah, normally if you have say 3 turbines, and if the 4-bay tank, if it is a low head project, then you can start, rather than having a bifurcation, that is bringing one pipe and dividing into 3 later, you can bring all 3 pipes on the one 4-bay tank, that is economical, right. But if it is a long penstock, it is more economical to build one penstock and then divide it near the powerhouse, it will be more economical. It depends upon the head of the project and the length of the penstock, etc. So, I have seen very long penstocks and then they divide into 3 or 4, but short penstocks, then you can, if you have multiple machines, then better to have straight away from the same 4-bay tank pipes, more economical.
Thank you, sir.
Excuse me, sir. Hello, sir.
Yes, I
Hello,
can.
sir.
Yeah, I can hear you.
Yes, sir. This is Manbir from Punjab. Sir, I just want to know the what type of the data we need to design the dimensions of the penstock beforehand. Who is providing the layout for the penstock?
Yeah,
Civil engineer or hydropower engineer is to decide.
Yeah, that's a good question. The question is, if you, who will decide the number of bends and the profile, etc. That will be done by a detailed survey of the profile. So, they will do the surveyor will give you the various surveyor will give you from the forebay tank, right, down to the powerhouse, what is the earth profile,
Is right.
like that, right. So, accordingly you will have bends.
Right.
So, it is the surveyor will the survey team will give you this profile, but of course, sometimes there may be a big rock here which you can't take, then you might have a horizontal bend also going around it, or you may avoid it. So, you have to look at all these ground features and decide the final route of the penstock, right, final route of the penstock.
Right. So survey engineer is basically providing the profile of the penstock, and
So,
then hydropower engineer is deciding the dimensions of the
that's right,
penstock.
that's right. Yeah. In reality,
Right. And
the hydropower engineer will
yeah,
employ a surveyor to
right,
first get this profile.
right, right. Thank you, sir. Thank you.
Okay, okay.